So let's talk about this velocity vector a little bit more, and in particular its relation to the so-called tangent line. When we have a parameterized curve, a function with one input and several outputs, it has a tangent line potentially at each position. Just like the graph of a two-variable function can have tangent planes, or just like the graph of a single variable function can have a tangent line. And what the tangent line does is it's a line that's parallel to the velocity vector. So at any given point in time, the tangent line is telling us, the direction of travel of the object at that exact position in time, like so. It's parallel to the velocity vector. And here's a formula for the tangent line at the time A. It says that the tangent line is equal to our position, c of A, plus our velocity times t minus a. This gives us a formula for a parameterized line. And this is, if you like, this is also the formula for the linear approximation. We could write this as c of a plus dc evaluated at a times t minus a. And this is the formula for the linear approximation. It tells us the closest possible linear function to the function c near the time t equals a. And what it does is it gives us a parameterized line that's as close as possible, and it tells us what would happen physically if we kind of stopped acting by any kind of force and just let the object start to drift at that particular point in time. So if you like, if we're imagining this parameterized curve as some kind of object moving through space, and at some point we just kind of take an object that they're holding and let it fall and let it drift off, the tangent line parameterization tells us where that object will be at any particular position in time. So here's an example. Here's a parameterized curve c of t. It's equal to t squared minus 1 comma t cubed minus t. As time goes on, it starts in this lower right corner and travels along this arc that loops around and then goes back towards the upper right eventually. It crosses the same position twice. It goes through the point 0, 0 twice, once at time 1 and once at time minus 1. If we calculate the velocity vectors, though, at time minus 1, the velocity vector, let's show how we calculate that. C prime of t, our velocity, is given by just taking the derivative with respect to t. We get 2t and 3t squared minus 1. That's our velocity at any particular point in time. At time minus 1, we're getting minus 2 comma 2. That velocity vector points in this direction. So at time minus 1, we can see that our object is moving kind of to the northwest. And as we travel around and come back to the same point, at time 1, when we again cross this, the velocity vector is pointing now in the direction of 2, 2. It's pointing to the northeast in a different direction. So even though we have the same position, our velocity is very different at those 2 points. We're going to have 2 different tangent lines. And we have this warning up top to remember that because we have this parameterized curve, it describes motion. It doesn't just describe this shape we see at the right, it also tells us where we are at each exact point in time. And we could also go and we could say, what's c prime of 0? Well, c prime of 0 is going to be 0, 3 times 0 minus 1. So minus 1 is going to be a vector that points downward like this. So it tells us exactly how fast we're going at each of these times as well. At this time, we're going with speed 1 because the length of this vector is 1, whereas these two vectors, 2, 2, and minus 2, 2, those both have length equal to the square root of 8. So this one has speed square root of 8, and this one has speed square root of 8, because these two vectors both have length equal to the square root of 2 squared plus 2 squared equals square root 8. So those speeds are slightly faster. It's telling us exactly how the speed changes as well as the position changes when we take things into account.